Hi, we are going to see the problems related with magnetism and matter. Basic properties of earth magnetic elements. Dip or inclination, magnetic declination, horizontal component of earth magnetic field. These are the elements of earth magnetic field. Then relation connecting force and the magnetic induction. F is equal to mb. And what is called the magnetic moment related with magnetic pole strength. Magnetic field along axial line due to a bar magnet. Magnetic field along equatorial line due to a bar magnet. Then we are going to discuss the types of magnets, dia, para and ferromagnets. Relation connecting susceptibility and permeability. Magnetic permeability, magnetic susceptibility, that relation. So all these things you are going to see few problems related to that. Okay. To start with, if earth magnetic field approximates the field due to a dipole of magnetic moment 8 into 10 power 22 joules per Tesla or ampere meter square, then calculate magnetic induction. Earth magnetic field, basic formula, B is equal to mu naught by 4 pi m by d cube or m by r cube. This is problem related with earth magnetic field. So the distance here is nothing but radius of the earth. Okay. So B is equal to mu naught, that is 4 pi into 10 power minus 7 by 4 pi into what is magnetic moment? 8 into 10 power 22 by r cube, that is nothing but radius of the earth, 6,400 kilometer. 4 pi cancels. This is 10 power 5 the whole cube, 10 power 15. 22 minus 15 is 10 power 15. 10 power 15, 10 power 15 cancels. So 8 by 64 cube. That is 0.305 into 10 power minus 4 Tesla or 0.305 Gauss. 10 power minus 4 Tesla is 1 Gauss. Okay. This is the first problem. Second one. A short bar magnet placed with its axis at 30 degree with uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 power minus 2 joules. What is the magnitude of magnetic moment? Torque experienced by the magnet. Formula, torque tau is equal to mb sin theta. Question is, what is the magnetic moment? So we have to write m is equal to tau by b sin theta. Tau. Torque is 4.5 into 10 power minus 2 divided by B is 0.25 into sin 30. Okay. So m is equal to 4.5 into 10 power minus 2 by 0.25 is 1 by 4. Sin 30 is half. So 8 into 4.5 into 10 power minus 2. So that should be 0.36 this is. So 0.36 ampere meter square. Joules per Tesla or ampere meter square, both are correct. Okay. Next, third problem. A short bar magnet of magnetic moment M is equal to 0.32 joules per Tesla is placed in a uniform magnetic field of 0.15 Tesla. If the bar is free to rotate in a plane of the field, which orientation corresponds to its stable and unstable equilibrium. What is the potential energy of the magnet in each case? First is stable equilibrium. Bar magnet is aligned along the magnetic field, means stable equilibrium. Bar magnet is aligned along the magnetic field. That is called stable equilibrium. Unstable means reverse. It is not aligned. That means it is opposite. Aligned. Not aligned means it is in the opposite direction. That is the meaning. So basic formula for potential energy is U is equal to minus mb cos theta. M is called magnetic moment. That value 0.32 into magnetic induction 0.15 Tesla into cos 0. Cos 0 is 1. So the answer is 4.8 into 10 power minus 2 joules. This is energy, so joules. Okay. Unstable equilibrium means it is aligned in the opposite direction. Aligned in the same direction means theta 0. Aligned in the opposite direction. In that sense, magnet is aligned along with the magnetic field. Magnet is aligned in the opposite direction of magnetic field. That is unstable equilibrium. So U will be minus mb cos theta dash. That is cos 180. Cos 180 is minus 1. So same answer. We will get 4.8 in 10 power minus 2 plus. There it is negative. Here it is positive value. Okay. Fourth problem. A closely wound solenoid of 800 turns, area of cross section 2.5 into 10 power minus 4 meter square, carries a current of 3 ampere. Explain the sense in which it acts like a bar magnet. What is the associated magnetic moment? A closely wound solenoid, number of turns 800. Area of cross section 2.5 10 power minus 4. Current 3 ampere. Explain the sense in which it acts like a bar magnet. Any current carrying conductor acts like a bar magnet because the magnetic line lies along its axis. That is, this is a solenoid carrying current clockwise. So the magnetic field will be along its axis, along its center. So it acts like a bar magnet. You can explain this concept using end rule. End rule means if the current flows in the clockwise direction, then nearer end is south pole, farther end is north pole. If the current flows in the anti-clockwise direction, nearer end is north pole, farther end is south pole, reverse. You can keep this like this, easy to remember. English letter S. So it comes up, it ends up with clockwise. So nearer end is south. Instead of writing this N like this, stylish N like this. So anti-clockwise. Anti-clockwise means nearer end is north pole. This is called end rule. So definitely a current carrying coil acts like a bar magnet. Okay. That is the first question. Second question, you're asked to calculate the magnetic moment. M is equal to NIA. Capital M is equal to NIA. N is called the number of turns. In our case, it is 800. Into current is 3 ampere. Into area 2.5 10 power minus 4 meter square. Simplify, you are getting 0.6 ampere meter square. 0.6 ampere meter square is the value of magnetic moment. Okay. Fifth problem. If the current carrying solenoid of magnetic moment 0.6 ampere meter square is free to turn the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied, what is the magnitude of the torque which makes an angle of 30 degrees with the direction of applied field? Magnetic moment is given. Magnetic field of induction 0.25 Tesla, angle 30 degree. You have to calculate the torque. Straight problem. Torque experienced by the magnet when it is placed in a magnetic field. Electrostatics, we have studied torque experienced by a dipole placed in electric field. Tau is equal to PE sin theta. P is called electric dipole moment. E is the strength of electric field. Here, same, but MB sin theta. There, it is electric dipole moment. This is magnetic dipole. M you can write, or you can put PM, magnetic dipole moment. Anything you can write. There, electric field E, here magnetic field B. Same concept. Magnetic moment is 0.6. Magnetic induction, field of induction is 0.25 into sin 30. 6 into 25 into half into 10 power minus 3. 6 into, that is 3. 75 into 10 power minus 3. Newton meter. Or 7.5 10 power minus 2. Anything you can write. Newton meter or joules. Okay. Then, sixth problem. A bar magnet of magnetic moment 1.5 ampere meter square lies aligned with the direction of magnetic field 0.22 Tesla. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field of direction, opposite to the field of direction? What is the amount of work required by the external torque to turn the magnet normal to the field, opposite to the field? What are the data? Magnetic moment given, magnetic field of induction given. Same concept. What is the torque in both the cases? First part, you have to calculate what is the amount of work required. So you have to calculate the energy. Second, you have to calculate the torque in both the cases. First, we'll calculate the work done or energy. Initial angle between the axis and magnetic field, θ1 is 0. Final angle should be 90. Because the question is work required to make magnetic moment normal to the field. Initially it is along the direction, so theta is equal to 0. Now you are rotating, so normal to the field. So theta is equal to 90, theta 2, theta 1 0, theta 2 90. So work done or energy formula minus mb cos theta 2 minus cos theta 1. Magnetic moment 1.5 into 0.22 into cos theta 2 cos 90 minus cos 0. Cos 90 is 0, cos 0 is 1, so minus or minus plus 1.5 into 0.22. So that should be 0.33 joules. Same they have asked, aligned opposite to the field. Aligned along the direction means theta 0. Opposite to the field means theta is equal to 180. So this is normal to the field. Opposite direction means theta 180. W dash is minus mb cos 180 minus cos 0 minus 1.5 into 0.22 into cos 180 is minus 1, cos 0 is 1. So minus 1 minus 1 minus 2. 2 minus minus plus 3 into 0.22. 0.66 joules. This is second part. Okay. Now, second subdivision. First subdivision, they have asked what is the work done along the axis, normal when it is rotating, opposite direction, what is the work done, they have asked. Second part of the question is calculate the torque in both the cases. What is torque formula? Just now we have seen torque. Torque tau is equal to, first case, tau is equal to mb sin theta. Here theta 1, theta 2 both are 90. So I can write tau is equal to MB, that is 1.5 into 0.22. 1.5 into 0.22 straight to 0.33 joules. Next, theta 1, theta 2 both are 180 here. So tau is equal to MB sin theta. Here theta is 90 means sin 90 is 1. So directly we have written 1. Whereas second case sin 180 means 0. So torque is 0 when it is aligned opposite direction of the field. Okay, fine. Next, seventh problem. A closely wound solenoid of 2000 turns, area of cross section 1.6 into 10 power minus 4 meter square, carrying a current of 0.4 ampere, is suspended through its center, allowing it to turn in a horizontal plane. What is the magnetic moment associated with that? What is the force and torque on the solenoid if uniform horizontal magnetic field of 7.5 into 10 power minus 2 Tesla is set up at an angle of 30 degrees with the axis of the solenoid? What we have seen before only we are going to do again. First one, magnetic moment. Magnetic moment NIA or NAI, anything. Number of turns is 2000. Current passing through 1.6. Current passing through is 4 ampere. Area is 1.6 10 power minus 4 Tesla. 2 into 4, 8. 8 into 1.6. 12.8. 10 power minus 1. So that is 1.28 ampere meter square. Straight. Next, we have to calculate the torque. Torque tau is equal to MB sin theta. M is 1.28. B given as 7.5 into 10 power minus 2 into sin 30. Aligned along 30 degree with the axis. So sin 30. Straight. Simplify 4.8 into 10 power minus 2 torque. So Newton meter or joules. Correct? Instead of calculating directly, first we'll calculate the magnetic moment, then we are substituting that value. That's all. Okay? Fine. Next step. Eighth problem. A short bar magnet has a magnetic moment of 0.48 ampere meter square. Give the direction and magnitude of magnetic field produced by the magnet at a distance of 10 centimeter from the center of the magnet along the axis and along the equatorial line. Magnetic field along the axial line, B axial, mu naught by 4 pi m by r cube or m by d cube. 4 pi into 10 power minus 7. Magnetic moment is, this is axial line means 2m. Equatorial line means m by d cube. So this is axial line, so 2m by d cube. Short bar magnet only this formula. Long magnet means 2md by d square minus L square, the whole square in denominator. Since L is small, we are neglecting. This is the final formula. Okay, that we have seen in the derivation. Into 2 into magnetic moment value 0.48 by 4 pi. Distance is 10 centimeter, that is 0.1 meter. Value 0.96. 2 into 0.48, 0.96. This is 10 power minus 2. Numerator 10 power plus 2. So simplify. 0.96. 1 into 10 power minus 1 the whole square mark. So that should be 10 power minus 2. Numerator 10 power plus 2. 10 power minus 5 Tesla. For equatorial line, you know very well, for equatorial line, it is mu naught by 4 pi m by d cube. That means half of this value. Half of this value means you can write B axial by 2. 0.48 10 power minus 5 Tesla. Straight. Suppose equatorial line alone they are asking means you can write the formula mu naught by 4 pi m by d cube and then substitute. Since we have calculated axial line value, we need not do it again. We can simply put by 2. Okay. This is 8th problem. Question, they are asking the direction also. For axial line, it will be along south-north direction. East, west, north, south. So south to north. Equatorial line, it should be reverse. North to south. Perpendicular plane only we are getting. So axial line, equatorial line. This is north-south, that is south-north. Okay, 9th one. A ring of mean radius 15 centimeter has 3,500 turns wire wound on a ferromagnetic core of relative permeability 800. What is the magnetic field B in the core for a magnetizing current of 1.2 ampere? Radius 15 centimeter, 3,500 turns, relative permeability 800. You have to calculate magnetic field of induction B, current 1.2 ampere. B is equal to mu naught Ni by 2R. That is actual formula for air medium. Here they have given a core. So we have to write mu naught mu R Ni by 2R. That is 4 pi into 10 power minus 7 mu R 800 into number of turns 3,500, current 1.2 ampere, radius 15 centimeter. Two into 15 into 10 power minus 2. So it should be 4.48 Tesla. 4.48 Tesla. Magnetic induction value. Straight. 10th one. Mu naught Ni by 2R. that's okay. Next step. Particle having a mass m, charge q, accelerated through a potential difference capital V. Find the force experienced when it is kept under perpendicular magnetic field. You know very well magnetic field force, that is called the Lorentz force, BQV sin theta. For a single electron, it is BeV sin theta. When the particle enters a magnetic field having some velocity, the work done by the particle is zero. It experiences a circular path. So, circular path means automatically centripetal force will come into the factor. So, the velocity here, that means we are equating mv square by r with the BQV. That is first part. Another part we have to equate with the electric field also. Electric field BeV is E into E is equal to BeV. The velocity is here E by B. BeV is equal to E into E, cancels, V is equal to E by V. This is the velocity. But potential difference is given here. Electric field versus potential difference formula, E is equal to V by D. Capital V is nothing but potential difference. Small v is nothing but velocity. So, simplifying, this is velocity. Capital V, here it is V by D. Simplifying, the velocity value of this is V is equal to root of 2qV by B by M. This is velocity in which the particle is moving in an electric field. Okay. Therefore, magnetic Lorentz force, that is question, BQV sin 90. So, BQV, F is equal to BQ, V is root of 2QV by M. This is small v velocity, this is capital V potential. So, take this BQ inside the bracket, inside the square root, 2 into B square. Q will become Q square. Already one Q is there. QQ into V by M. This is the force experienced by the particle moving with the velocity V under the potential difference capital V. Okay. Fine. 11th problem. Calculate the magnetic dipole moment of a circular coil of radius 5 cm and 50 turns, carries a current of 3 ampere. Magnetic moment NIA or NAI, whatever it is. Capital M you can put, or P is suffix small m, this one. This is also called magnetic moment representation. So, number of turns 50. Current here is 3 ampere, and the radius 5 centimeter. So, pi r square (3.14) into 5 into 10 power minus 2 the whole square. Simplify, you are getting 1.2 ampere meter square. Straight. Okay. Next. 12th one. A thin insulated wire forms a plane spiral. N is equal to 100 tight turns, carrying a current of I 8 milliampere. The radii of inside and outside turns are 50 millimeter and 100 millimeter. Inside to outside radii 50 millimeter and 100 millimeter respectively. Calculate the magnetic induction at the center of the spiral. B is equal to mu naught Ni by 2R 4 pi into 10 power minus 7. Number of turns is 100. Current is 8 milliampere. 8 into 10 power minus 3. Here only 1 R is given. There inside to outside radius is given 100 millimeter and 50 millimeter. So average radius only we should take into account. This point is very important here. This is average radius 75 millimeter. (75) into 10 power minus 3. Okay, simplify, you are getting 6.7 into 10 power minus 6 Tesla or 6.7 micro Tesla. 10 power minus 6 is micro Tesla. Okay. 13th problem. A wire of length L carrying a current I along the y direction, current carrying in y direction, is kept in a magnetic field given by B vector is equal to B by root 3 I cap plus J cap plus K cap. Calculate the magnitude of Lorentz force. Right? Magnetic Lorentz force for a current carrying conductor is F is equal to IL vector cross B vector. Expanding magnitude means BIL sin theta. So F vector is equal to IL vector. What is that value? Current along the y direction. So IL J cap cross B vector given as B by root 3 into I cap plus J cap plus K cap. So first BIL by root 3 J cross I. J cross I means minus K. Sir, I, J, K. J cross I. J cross K means it is plus I. I cross J means it is plus K. K cross I means it is plus J. Because it is coming in the normal rotation. Here it is J cross I. That means you are skipping 1. When you are skipping 1 means it should put minus. So J cross I is minus K plus J cross J. J cross J is 0. Cross product 0. Next J cross K. J cross K, that is I. So F is equal to, I want only the magnitudes there. Magnitude means you can write BIL by root 3. This is root of 1 plus 1. So BIL root of 2 by 3. BIL root of 2 by 3 is the answer. Problem number 14. Two short bar magnets have magnetic moments 1.2 ampere meter square and 1 ampere meter square. They are kept on a horizontal table parallel to each other. Here one magnet, here one magnet. With the north pole pointing towards south. North pole of one pointing towards south of the other magnet. They have a common magnetic equator and separated by a distance of 20 centimeter. Calculate the resultant horizontal magnetic induction at the midpoint O of the line joining the centers. For first magnet along the equatorial line, first magnet, second magnet along the equatorial line, common point V1. So mu naught by 4 pi M1 by R cube. For second magnet, B2 is equal to mu naught by 4 pi M2 by R cube. In addition to that, earth magnetic field is also present. And BH is the earth horizontal component of earth magnetic field. So the resultant magnetic field should be B1 plus B2 plus BH. That should be mu naught by 4 pi R cube. That is constant. M1 plus M2 plus BH. 4 pi into 10 power minus 7 by 4 pi into the distance 10 centimeter. 10 into 10 power minus 2, the whole cube. 1.2 ampere meter square. 1 ampere meter square, that is the data given. Plus earth magnetic field 3.6 into 10 power minus 5 Tesla. Some cases they will write 3.88 into 10 power minus 5 Tesla. Some cases they will write 3.6 into 10 power minus. It is a constant value. Earth magnetic field that we will measure using tangent galvanometer. That value 3.88 10 power minus 5 Tesla. Some other case it is 3.6 10 power minus 5 Tesla. Simplify, you are getting 2.56 into 10 power minus 4 Tesla. 2.56 into 10 power minus 4 Tesla. Okay. 15th problem. Calculate the potential energy of magnetic dipole whose dipole moment is M is equal to minus 0.5 I cap plus 0.4 J cap ampere meter square. Magnetic induction 0.2 Tesla, 0.2 I Tesla. Kept in uniform magnetic field. Calculate the potential energy. That is the question. Potential energy is U is equal to minus MB sin theta minus 0.5 I cap M cross B, that's all. I cap plus 0.4 J cap into 0.2 I cap. So M dot B dot product means sin theta, cross product means cos theta. Okay. Value 0.5 into 2 because I dot I is 1 minus minus plus 0.5 into 0.2. I dot I is 1. That is 0.1 joule. Straight. 0.1 joule. Okay, ba? Fine. Second, that is 16th problem. Circular coil of cross-sectional area 0.1 centimeter square is kept in a uniform magnetic field of strength 0.2 Tesla. If the current in the coil is 3 ampere, plane of the loop is perpendicular to the direction of the field. Calculate total torque on the coil, total force, average force on each electron. Total torque. Torque tau is equal to mb sin theta. Magnetic moment is current into area. So BIA sin theta. So substituting the values of B, A and I. An important concept here, current in the coil 3 ampere, plane of the loop is perpendicular to the direction. Plane of the coil is perpendicular, but normal is along the axis. Normal is along the axis. Along the axis means theta is equal to 0. Here theta is equal to 0. So whatever you are substituting sin 0, answer is 0. Second, torque is equal to BIA sin theta. Question is, what is the force? Force is BIL sin theta, ma. This is BIA. This is BIL. BIL sin theta. Here also theta is equal to 0. So naturally the force is 0. And third case, average force required. BQV sin 90. BQV. Why? See here. Average force on each electron. The direction of movement of electron is along the direction or along the axis. It is, question is, current in the coil is 3 ampere and the plane of the loop is perpendicular to the direction of the magnetic field. So the direction of movement of the electron is along the field. Direction of movement of electron along the field means theta is equal to 0. Theta is equal to 90. Here theta is equal to 0. Electron movement is normal, perpendicular. So theta 90. So BQV sin 90. Electron normally moves with the drift velocity in a wire. So it is BD. You know very well, current and drift velocity equation I is equal to NEA VD. So I can write BQ VD is I by NEA. One electron means it is B. Cancel BI by NA. Substituting the values Bi by Na. Magnetic induction 0.2, current is 3 ampere, number of electrons or electron density 10 power 28, then A is 0.1 into 10 power minus 4. Simplify, you are getting 6 into 10 power 24 Newton. 6 into 10 power 24 Newton you are getting. A dot B is equal to AB cos theta. A cross B is equal to AB sin theta n cap. So cross product means sin theta. Dot product means cos theta. So when you say both the vectors are in the same direction, it is AA cos 0. AA cos 0 means cos 0 is 1. That is A square. A square is A. Same direction means theta is equal to 0. AA sin 0. Sin 0 is 0. Okay. So this basic concept. Work done. F vector dot S vector. That is Fs cos theta. Force and displacement are vectors, whereas work done is a scalar. Example, scalar product or dot product. Vector product means torque, R cross F. Rf sin theta n cap. Displacement, force, torque, all the three are vectors. So resultant torque will be in a direction perpendicular to both R and F. Okay, this concept you have to apply. While multiplying I cross I or I dot I, please think and do it. I dot I cross I j k. I cross j k, j cross k I, k cross I j, like that. I dot I dot I, 1. I dot I is 1. I cross I means it is 0. I cross I means it is 0. Why it is 0? Because sin 0. Sin 0 is 0. So this is a basic formula. A bar magnet is placed in uniform magnetic field whose strength is 0.8 Tesla. If the bar magnet is oriented at an angle of 30 degrees with the external field, you experience a torque of 0.2 Newton meter. Calculate the magnetic moment of the magnet. Magnetic field is 0.8 Tesla, angle 30 degree, torque 0.2 Newton meter. You have to calculate the magnetic moment. So 17 tau is equal to mb sin theta. M you have to calculate. Tau by b sin theta. You can write Pm or you can write M. Both are magnetic moment. Torque value 0.2 by B value 0.8 sin 30. 0.2 by 0.8 into sin 30 is half, 0.4. So 2 by 4, 1 by 2, that is 0.5 ampere meter square. Correct? So this is a magnetic moment we have calculated for a given value of torque and magnetic induction. Okay. So many combinations we have used in this chapter. Magnetism and its matter, or magnetism and its properties also you can say. So basic properties of magnetic materials or magnetism and matter, we have used different formulas and we have done the basic exercise. Okay. We'll continue with electromagnetic induction in the next class. Thank you. We'll continue.